In this video, we'll explore how to design a production machine learning system for a real-world privacy-critical application, automatically blurring human faces and license plates in Google Street View. This is a classic computer vision problem at massive scale, involving billions of high-resolution images, strict accuracy requirements, and continuous feedback loops from users. The following provides an overview of the key contents. We'll walk through how to frame this task as an ML problem, clarify requirements, prepare data, develop models, evaluate them, and finally serve predictions in production. By the end of the session, you'll gain practical insights into building scalable and reliable ML systems that operate in the wild, where user trust and privacy are non-negotiable. The problem is to design a system to automatically blur human faces and license plates in Google Street View. Here are some good questions to ask in the requirement clarification phase. Can users report images that are not correctly blurred? Do we have labeled data? Do we care about fairness and bias? Is latency an issue? Can we blur images offline? Now we'll walk through how we define the blurring task, detecting sensitive content like faces and license plates, as a formal machine learning problem. 1. ML objective. Identify objects in an image. Our core goal is to identify all instances of sensitive content in each image, faces, license plates, and possibly other identifiers. This means not just recognizing what is present in the image, but also where it is. 2. Input and output. Input: a high-resolution image captured by the Street View car. Output: a list of bounding boxes indicating the locations of sensitive objects. The class label for each bounding box, e.g., face, license plate, person, etc. The output needs to be highly reliable because we're dealing with privacy-sensitive content. 3. Two subproblems in one. The task breaks down into two core components. Object localization. Where is the object in the image? This is treated as a regression problem. We're predicting continuous bounding box coordinates, x, y, width, height. Object classification. What kind of object is it? This is a multi-class classification problem, assigning the correct label, face, plate, etc. to each detected region. So we need a model that can handle both tasks simultaneously. 4. Two types of neural network architectures. We can approach this task using two general families of models. Two-stage networks. These first use a region proposal network, RPN, to suggest likely object regions. Then a second stage classifies each region. Example, faster RCNN. Strength: typically higher accuracy, better for complex scenes. One-stage networks. These directly predict bounding boxes and class labels in a single pass. Example, YLOSSD. Strength: much faster, lower latency. Great for real-time or large-scale deployment like Street View. Depending on the trade-off between accuracy and speed, we'll choose an architecture that fits our needs, often starting with a one-stage model for efficiency and scaling up as needed. In summary, the Street View blurring task is a multitask learning problem. We use object detection models to solve a regression task for object location and a classification task for object type, all driven by a need for high performance and privacy guarantees. Before we can train any model to detect and blur sensitive content, we need to carefully prepare the right data. This phase includes both data engineering and feature engineering, which form the foundation of any effective computer vision system. 1. Data engineering. The model needs a labeled dataset. That means a large collection of Street View images where all sensitive objects are manually annotated. Each object, e.g., face, license plate, must have a bounding box and an associated class label. Annotation tools are often used by human labelers to draw boxes around these objects. The input data consists of raw Street View images, typically high-resolution photos taken at street level from various camera angles and lighting conditions. This data is collected at a massive scale, so quality control and consistency in labeling are critical. Without high-quality labeled data, the model will struggle to learn meaningful patterns, especially given the privacy-critical nature of the task. 2. Feature engineering. While deep learning models extract features automatically, we still apply standard image pre-processing to ensure consistency and quality. Resize images to a standard input shape. Normalize pixel values. Apply color corrections if needed. Data augmentation is especially important to make the model robust. Apply random transformations such as flips, rotations, crops, and brightness/contrast changes. This helps the model generalize to different conditions, for example, faces and shadows, tilted license plates, or partial occlusions. Data augmentation is crucial for simulating real-world variability in Street View imagery, helping the model detect sensitive content in diverse and sometimes difficult conditions. In summary, the quality and variety of the training data are essential. Accurate labels, smart augmentation, and consistent pre-processing ensure the model is well prepared to handle the real-world complexity of Street View imagery. To detect sensitive content like faces and license plates in complex street imagery, we choose a two-stage object detection architecture, which offers strong localization accuracy, something we can't compromise on in a privacy-critical system. Two-stage architecture. The model follows a two-step pipeline. Region Proposal Network. RPN proposes potential object-containing regions, a few hundred candidates per image. This reduces the search space. Classifier plus bounding box regressor. Each proposed region is then classified, face, license plate, etc., and the bounding box is fine-tuned. A common implementation is FasterRCNN, which integrates the RPN and classification network into a shared backbone, improving efficiency while maintaining high accuracy. Convolutional layers. The backbone of the network, e.g., ResNet, VGG, or MobileNet, uses convolutional neural networks, CNNs, to extract image features. Early layers detect low-level features, edges, textures. Deeper layers detect high-level patterns like faces or license plates. These features are shared by both the RPN and the classification head, allowing for efficient feature reuse. CNNs are a natural choice here due to their strong inductive bias for spatial hierarchies in images. Model training. Once the architecture is selected, we move to training the model using supervised learning on our labeled dataset. This involves several key steps. Forward propagation. The image passes through the CNN to generate a feature map. The RPN takes the feature map and proposes candidate regions, anchor boxes. The ROI pooling layer extracts fixed-size feature maps from each region. Finally, the classification head outputs a class prediction, e.g., face, license plate, background, refined bounding box coordinates, loss calculation. The training objective is to minimize the total loss, which has two parts. Regression loss, e.g., smooth L1 loss or IOU-based loss, measures how accurately the predicted bounding boxes align with ground truth boxes. Penalizes errors in X/Y position, width, and height. Classification loss, e.g., softmax cross-entropy. Penalizes incorrect predictions for object classes. Encourages high confidence for the correct class. These losses are weighted and summed to form a single objective function for training. Backward propagation. The total loss is used to compute gradients with respect to all network parameters. We use backpropagation to update weights across the CNN, RPN, and classification head. Optimizers like SGD with momentum or atom are used to iteratively reduce the loss. Proper tuning of the learning rate, weight decay, and batch size is crucial to convergence. Key training considerations. Imbalanced data, faces and plates may be rare in some areas. We use sampling strategies like hard negative mining or focal loss to address this. Overfitting. We monitor validation performance and use regularization techniques like dropout and data augmentation. Transfer learning. We may initialize from a model pre-trained on COCO or open images and fine-tune on Street View. Specific data. To summarize, We select a two-stage object detector with convolutional backbones for precise object localization and classification. Training involves careful design of the loss function and backpropagation loop, with a focus on privacy-driven accuracy, robustness to variability, and scalability. Once the model is trained, it's critical to rigorously evaluate its performance, both offline during development and online after deployment. Our goal is to ensure high detection accuracy of sensitive objects with minimal false positives and negatives, since these can directly affect user privacy and trust. Intersection over union, IOU. IOU is the foundational metric we use to evaluate how well our model predicts the location of sensitive objects. It's defined as the ratio between the overlap area of the predicted bounding box and the ground truth box, divided by their union area. A prediction is considered correct if its IOU exceeds a certain threshold, typically 0.5 or 0.75, depending on how strict we want to be. Higher IOU means more accurate localization. For this system, higher precision is key, especially for faces and license plates. Offline metric, mean average precision, MAP. During development, we use MAP as our primary offline evaluation metric. MAP summarizes the model's precision. Recall curve across all object classes and IOU thresholds. Precision measures how many predicted bounding boxes were correct. Recall measures how many actual objects were successfully detected. We compute average precision, AP, for each class, e.g., face, plate, then average them to get MAP. This gives us a single number that reflects both detection accuracy and consistency. A high MAP score means our model is not only accurate, but reliably finds all objects across various image conditions. Online metric, number of user complaints. After deployment, we rely on real-world feedback. A key online metric is the number of user complaints about unblurred sensitive content. These complaints are logged by users who spot faces or license plates that were not properly blurred. While it's a coarse signal, it gives us a practical, user-facing measure of system effectiveness. Even a small number of complaints can be serious, so we monitor this metric closely and treat it as a signal for retraining or manual review. To sum up, we use IOU for precise bounding box evaluation, MAP for overall model performance during development, and user complaints as a live signal of real-world quality. Together, these ensure we maintain high standards of accuracy, privacy, and public trust. Once we've trained and evaluated the model, we need to operationalize it. That means embedding it into a scalable serving pipeline. This allows us to process billions of Street View images at scale while continuously improving the model based on real-world data. Batch prediction pipeline. First, let's talk about how we serve predictions at scale for massive datasets. Pre-processing. Each Street View image goes through a pre-processing stage. Resize or normalize the image. Convert to the input format expected by the model. Potentially break large panoramas into tiles to fit GPU memory limits. Blurring service. The model is served through a blurring service. It detects faces, license plates, and other sensitive content. The output is a set of predicted bounding boxes and associated class scores. Blurring is applied directly to the identified regions. Non-maximum suppression, NMS. Since the model may generate multiple overlapping bounding boxes for the same object, we apply non-maximum suppression. NMS removes redundant boxes by keeping only the highest confidence box per object. It helps clean up predictions and ensures we don't overblur or underblur. This entire batch pipeline runs on massive clusters, often in distributed fashion, to process millions of images per day. Data pipeline. In parallel, we run a data pipeline that supports model improvement and error correction. Processing user complaints. When users report that sensitive content wasn't properly blurred, those images are flagged and routed into the pipeline. These become important feedback for identifying failure modes. Generating new training data. Complaints and edge cases are used to generate new labeled training samples. This helps the model adapt to rare cases or visual patterns not well represented in the original dataset. Preparing training data for the model. This involves cleaning labels, applying augmentations, splitting data into training, validation, and test sets. The more representative and up-to-date our data, the more robust our model becomes. Hard negative mining. A key technique here is hard negative mining. When the model incorrectly labels a background region as a face or plate, we turn it into a negative training example. These hard cases help the model learn sharper decision boundaries and reduce false positives. In summary, we have two pipelines: a batch prediction pipeline that performs detection and blurring at scale, a data pipeline that ingests real-world signals, like complaints, turns them into training data, and improves the model over time. Together, they form a feedback loop that allows Google Street View's blurring system to get smarter, safer, and more accurate over time.